Hi everyone, welcome back. We're going to talk today about inferential statistics, and it is going to be a little bit of a leap from talking about descriptive statistics. I hope it's not too big of a leap. And your textbook does a fairly good job of describing the difference between inferential statistics and descriptive statistics. I'm going to do my best to clarify on what is actually a fairly complex concept and kind of whittle it down to the pieces that we need to know as analysts doing applied research. And that's really a focus in this course, is that there is a lot to know in statistics that underpins a lot of what we do. And I'm going to share with you what you need to know in order to perform statistical tasks. If you want to go into more depth, you can certainly read from your textbook, or you can read other information from other sources. But I don't want to hinder us from moving forward in statistics by bogging us down with too much of probability theory and some of the theoretical background, because in the day-to-day work that we do as analysts and statisticians, they aren't things that are necessarily that important to keep in mind. However, I am going to introduce some concepts that may either resonate from previous courses or may be totally new, and we'll do our best to get through some of the more theoretical pieces. So we've already calculated descriptive statistics for a sample. We've done things like a mean, a median, maybe a proportion. And we could just be interested in what's happening within our sample. So for example, if I was the head of a hospital, I might say, hey, what's going on with my patient population? And look through the data and say, okay, well, the average age in our clinic is 70 years old, and the average distance they live from the hospital is 20 miles or something like that. And that's interesting. But normally when we're doing research, we don't want to just know about a particular hospital. We want to know something about a much larger population. We want to know something that might be true for the United States, or for our city or our state, or whatever population we're trying to learn something about. And we have to design a study that's appropriate for making those kinds of inferences. But let's assume that we have. Let's assume that we have a large enough sample that it's representative and that we randomly selected participants. And that goes more into methodology than statistics. So we have this sample, and it's large, and it's representative. So we're now calculating things like means and proportions with a little bit different intent. The intent here is to make some inferences about the population, to say something about the broader population based on what we observe in our sample. Okay, and that's usually the goal of research. And that is actually what distinguishes research from, say, just looking at a process within our own hospital. And if we're needing to get something approved for IRB review to do research, it's when we're trying to create generalizable knowledge, right? And so anytime we're starting to do point estimation or saying something about a population, we are starting to move in towards research as opposed to pure descriptive work. So point estimation, we use the sample data to calculate a point estimate of an unknown population parameter. So for example, I may want to know what is the typical age of a patient who presents with concussion in emergency departments. And we're actually going to look at some of this data, so this is why I chose this example. But so what's a typical age? So I might have some guesses based on my own experience in a specific clinic, but I want to know on average across the United States, what is the average age of somebody who presents with concussion? Well, the way I would go about this is I might obtain data from a random sample of hospitals across the country, have a large enough sample size that I could get a pretty good guess as to what the typical or average age is in the population. I want to be careful to include cities and rural areas, different states, different demographics in the sample. But if I get a big enough sample and it's representative, I'm going to get a pretty good guess, okay? And so in that case, we're trying to use what we obtain in our sample to say something about the larger population. Why would we want to know something like that? Well, it may provide opportunities for prevention. So if we know that the typical age of somebody who has a concussion is school age, under 20 years old, then we may have to do more work to prevent that in that population. just knowing the average can help us figure out where our targets will be. But maybe we also want to see if there's been some changes in time over time in something like the proportion of patients who are adolescents versus young adults, and what are the underlying causes of these changes. And that gets more into the bivariate analysis that we're going to look at later. So we allow for a certain amount of uncertainty around our estimates. So if I obtain an estimate that the average age is 20.3, it sounds very scientific and accurate, but I know that it's going to be not perfectly what the true population answer is. But I can, however, create confidence intervals around that estimate to say, okay, this is where the true population percentage is likely to fall. And you often see this reported with things like prevalence, that the estimated prevalence of asthma in the population is between 8 and 10%. Notice they don't say that it is absolutely 9%. It's somewhere in that range. And that's kind of confidence interval type thinking, or margin of error type thinking, where we're saying there's certain uncertainty around this parameter, but we're pretty certain this is where it falls. We can also derive multiple subsample estimates from the same sample, meaning, let's say I wanted to say, well, is there a difference between men and women, or boys and girls, in terms of the average age of presentation for some disease or whatever it is I'm interested in? I could also create confidence intervals around those subgroups. Normally, when we're doing studies, we're not trying to estimate tons of different things at once, but if we're doing something like a national healthcare utilization survey or other types of national data sources, we may try to estimate all kinds of things in the population, especially for prevalence and incidence. Okay, so we calculate our point estimate. That's easy. We already saw how to calculate a mean. Just take the sum of values and divide it by the sample size to get our means. We're ready to go. Proportion is just the frequency divided by the total population. Express that either as a proportion or a percentage. And so those are really easy to calculate, right? But what we want to do next is say, how likely, or where is the population value likely to fall, assuming we have a representative sample? Well, the way we do this is around our point estimate, we have to calculate a margin of error. And for many of the confidence intervals that we often use in public health literature in particular, we're going to create 95% confidence intervals around the estimate. What is it? Well, a 95% confidence interval says we can be 95% sure that the true population value falls somewhere within these bounds. 5% of the time we're wrong, but 95% of the time we're going to be right, that it falls within these bounds. And this is going to come up again when we talk about p-values, is that we're allowing for a certain level of uncertainty. It's the nature of statistics to allow for a certain level of uncertainty, but we're willing to tolerate a certain amount of uncertainty. So I mentioned 95% confidence intervals because your textbook is going to go into how to calculate 99% confidence intervals, 90% confidence intervals. I will tell you right now that in the statistical literature or the research literature, 95% confidence intervals are the norm. And so while conceptually it's reasonable to know how to calculate all these different confidence intervals, what you will most likely report is a 95% confidence interval. So I'm going to show you how to do that. So we're going to start by looking at a simple example where we might try to calculate a confidence around a mean. So we have a relatively large sample, and this time we truly have systolic blood pressure, was 127.3 with a standard deviation of 19. Okay, that's nice out to report in our descriptive statistics. However, if I would like to convert that into a confidence interval around that estimate, so this is now making the leap to saying that we think that this value of 127.3, based on a sample of 3,534 patients, fairly large, is probably pretty close to the population mean. How close is it? So in the formula for a 95% confidence interval, some of this is going to be familiar and some of it not. So the S here is the standard deviation, which we can calculate directly in our data. We also have the sample size. We're taking the square root of the sample size in the denominator. And we're multiplying it by this z value, the z statistic, which actually comes from a standard normal distribution. And it's a value that represents how many standard deviations it is from the mean. And I will show you that in more detail. But for now, let's go through the calculation, and then I'll show you where this 1.96 value comes from. So the mean of 127.3 plus or minus 0.63. That 0.63 is simply making this calculation here, 1.96 times, in parentheses, 19 divided by the square root of 3,534. So we get this 0.63. And this 95% confidence interval goes from a lower bound of 126.7 to an upper bound of 127.9. Well, what does that say? And this is a 95% confidence interval. We would say that we can be 95% confident that the true population mean falls between 126.7 and 127.9. Okay. Notice if we had had a smaller sample size, this, because it's in the denominator, this value would become larger and our confidence intervals would become wider. Okay, so sample size is really important in calculating the width of the confidence interval. The standard deviation is also important. So how much variability there is overall in systolic blood pressure will also help determine the confidence interval. Probably the most important thing, or the most important thing, is the sample size. Okay, so if we were to have half that sample, our confidence intervals would end up being much, much wider. So we can be 95% confident that the true population systolic blood pressure is somewhere between 126.7 and 127.9. And that may not sound very satisfying. Be like, well, I'd like to know what the actual value is. Well, the only way to know the actual value is to take systolic blood pressures on everyone in the population, which, if any of you were nurses or in healthcare, that would be a big task, even though it doesn't, take that long to do blood pressure. We don't have that instantaneously. So why do that when we can get a really good estimate or very close to the truth by simply taking a sample? Okay, so that's where we can learn a lot from just a small number of cases, in this case, 3,000. Compared to 350 million people who live, let's say, in the United States. Okay, now we can calculate a confidence interval for a smaller sample size. Normally, we don't really need to do this because we should have a sample that's much larger than 30 people to be making a population inference. But if we were to use a small sample confidence interval, we could use the T distribution, which has a slightly different value for that statistic. But we're going to use this formula for calculating a confidence interval around a mean. So this 1.96 comes from the standard normal distribution. And the standard normal distribution has a mean of 0 and a standard deviation of 1. And this is a purely theoretical distribution. But what it says is that with a standard deviation of 1, about 68% of values are going to fall within 1 standard deviation, and 95% of values will fall within 2 standard deviations, and about 99% of values will fall within 3 standard deviations. Well, if we think about that in terms of percentiles, and we look out here towards the tails of the distribution, we can say at what point are we getting into the extremes or extremes of this distribution. And this distribution is actually a probability distribution. So if we were to randomly select a point from this distribution, we're most likely to get something in here. We're far less likely to get a value chosen from out here in the tails if we were just to take a random sample. So theoretically, this probability distribution, we can calculate a value, in this case, 1.96. So that cuts off 2.5% of the distribution at both ends. when you add those together, that's 5%. And then subtract that from 100%, that's where we get 95%. Confused? So that 1.96 represents the 97.5%, 97.5 percentile, or the 2.5th percentile on the low end, okay? Does that make sense to you? Maybe not. But what you need to know from this is that the 1.96 value comes from this theoretical distribution that suggests that if we were to take random samples from a population, it should take on a normal distribution like we see here. And then we can, from this, make a determination as how likely is it to have a certain value obtained from that. Okay, moving on to the confidence interval for a proportion. Again, it's very easy to describe the sample and say we've got 1,219 patients who are on a hypertensive medication out of 3,532 in our sample for 34.5%. Okay, so proportion, we would write it this way. As a percentage, that would be 34.5%. We're going to keep it in the form of a proportion for purposes of calculating a confidence interval. So again, notice here that Z value, and if we're calculating a 95% confidence interval, so again, that Z value, we're going to plug in 1.96 here, which we can look up from a table, but I will assure you that we're going to use the 1.96 for 95% confidence intervals. And what we plug in here is the proportion that we observed, 1 minus that proportion, and divide that by the sample size, and then take the square root. So slightly different formula, but very similar concept. And again, our population size is going to be the most important determinant of the width of the confidence interval. We don't have a measure of variance with a proportion. However, how far or how close it is to 50% versus 0% and 100% will have some influence on the size of the confidence interval. What's most important for the confidence interval of a proportion is the sample size. So we can see in this example, we've got 0.345 plus or minus 0.016. And just like we interpreted the confidence interval for a proportion, we can say that the true population proportion falls somewhere between 32.9% and 36.1%. Okay, notice that's about a 4% span here for the confidence interval, but we've got a fairly large sample size, so we can say the true population percentage that are on an antihypertensive medication is somewhere between 32% and 36%. Okay, and that might be close enough if that was our goal. But that would be how we would report out in terms of where we think the population value actually falls. Okay, so that's for a proportion. We can also calculate a confidence interval around a difference in two means, and this is already getting us a little into bivariate analysis, which I'm saving for next week. But conceptually, we could calculate a difference between two means, let's say between men and women. We would actually apply the same sample size and Z statistic to that mean to calculate our confidence intervals. So our mean difference was 12.7, standard deviation was 8.9. We plug that into our formula, add or subtract that from our estimate. And so the difference falls somewhere between -14 and -10. Well, so what that shows us is that we can be 95% confident that there's a difference somewhere between 10 and 14 points. So we would interpret this confidence interval as saying that the true population difference falls somewhere between -10.7 and -14.1. And so it does appear in this case that there's some difference between these two groups. We can't be exact about how far apart they are, but it's somewhere between 10.7 and 14.1 points, which we'll learn as we go forward actually suggests that there is a statistically significant difference between these means, but we're not quite there as far as talking about that yet. Likewise, we can calculate a difference between two proportions in terms of a confidence interval. Again, slightly different formula. We're still going to use that Z statistic from a standard normal distribution. Okay, so if we had a treatment group 1 where 46% had a response to treatment, treatment group 2, 22% had a response to treatment, we could calculate a confidence interval around that difference. So 0.46 minus 0.22, which are the proportions that correspond to those percentages, is 0.24. Okay, and then we plug in our proportions for each group here. We end up with plus or minus 0.18. So the difference between the two proportions, 0.24 plus or minus 0.18. So the true difference is somewhere between a minuscule difference of 0.06 and a slightly larger difference of 0.42 in terms of the difference. So it does seem that there is some effect here of treatment in terms of response. And we can see that we could be 95% confident that there is some difference here. That's a non-zero difference, somewhere between 0.06 and 0.42. I will not have you calculate these by hand. I simply wanted to show you that for any point estimate that we create, we're also going to calculate a confidence interval around that estimate, knowing that it does not perfectly reflect what's in the true population. However, we can, with confidence intervals, express where that population value is likely to fall. Okay, so some other confidence intervals that we might be interested in calculating. We already saw the difference between two means, difference between two proportions. When we start getting into logistic regression, we will start to estimate what are called odds ratios. Odds ratios can be calculated also from 2x2 tables, but we can use logistic regression to obtain an odds ratio. And we will calculate confidence intervals around those. And again, that would be to say where the true risk of some exposure falls in the population. And for these other parameters that we are trying to estimate, it's much easier to use some sort of statistical calculator or software, but they're conceptually very similar. And we'll often be plugging in similar values for the Z distribution to these confidence intervals. It also depends on what the estimate is. But conceptually, these are very similar.